You know, every single star you see in the night sky is in a battle for its life. It's this colossal, lifelong tug of war between two unimaginable forces. And here's the thing, it's a battle that every star eventually loses. What happens in that final moment of defeat is one of the most violent and, frankly, one of the most important events in the entire universe. And it all comes down to a single cosmic breaking point. Really, this whole cosmic story boils down to one simple question. What is the absolute maximum weight a dead star can carry before it just blows itself to pieces? Now, it sounds straightforward, but the answer to this question defines everything. How stars die, how the elements needed for life get made, and even how we measure the sheer scale of the universe itself. So let's find out what that ultimate weight limit is. To get to that answer, we first have to understand the main conflict that's raging inside every single star, day in and day out. It's this perfect, delicate balance that can last for billions and billions of years. So inside a star, you've got two major forces locked in an epic struggle. On one side, you have gravity, which is relentless. It's always trying to crush the star down into the tiniest point possible. But fighting back is the incredible energy from nuclear fusion happening at its core. This creates a constant outward push, a massive explosion that perfectly counteracts gravity's crush. And as long as that star has fuel to burn, these two forces are in a complete stalemate. But nothing lasts forever. Eventually, that fuel runs out. For stars like our sun, the fusion engine just kind of sputters and dies. And that powerful outward push, it just vanishes. And gravity, which never sleeps, finally gets the upper hand. The star begins to collapse in on itself under its own immense weight. It's catastrophic. Now, you'd think that's the end of the story, right? Gravity just crushes the star into nothingness. But then, just when it seems like it's all over, something totally bizarre and amazing happens. A new kind of force emerges from the weird world of quantum mechanics to push back. And our new hero is called electron degeneracy pressure. And trust me, it is weird. It has absolutely nothing to do with heat or fusion or any of that. It's a pure quantum rule that basically says you can only cram so many electrons into a tiny space before they start pushing back with an incredible force. It's this pressure that suddenly halts gravity's crush and saves the star's core, which we now call a white dwarf. So how does this actually work? Well, imagine the star's core is like a giant stadium with a fixed number of seats. Gravity is trying to shove an infinite number of people, those are the electrons, into that stadium. At some point, every single seat is filled and you just physically cannot squeeze anyone else in. That pushback you'd get from the crowd, that's degeneracy pressure. For a while, physicists just figured this pressure was infinitely strong, that it could hold back any amount of gravity. But then, in the 1930s, this brilliant young physicist named Chandrasekhar was on a boat trip from India to England. And he started thinking about a question that, believe it or not, nobody had thought to ask. Is this pressure really infinitely strong? Chandrasekhar's logic here was a total game changer. He realized that as you add more and more mass, gravity squeezes that core even harder, and that forces the electrons to move faster and faster, getting them incredibly close to the speed of light. Now, thanks to Einstein's theory of relativity, he knew this changes everything. As the electrons approach light speed, the pressure they can exert doesn't keep up with the increasing crush of gravity. He did the math right there and came to a stunning conclusion. This quantum pressure isn't infinite after all. It has a breaking point. And this is the number, 1.44. Specifically, 1.44 times the mass of our own sun. This is it, the Chandrasekhar limit. It's the absolute final maximum mass that electron degeneracy pressure can possibly hold up. You add just one more ounce beyond that and the whole thing fails. So that's the crucial question, isn't it? What happens when that line is crossed? What happens when a white dwarf star gets a little too greedy and packs on just a little too much weight? Well, the most common way this goes down is in a binary star system. Picture a stable white dwarf orbiting a normal star. Over millions of years, its intense gravity can start siphoning off gas from its partner, kind of like a cosmic vampire. It slowly adds mass to itself, creeping closer and closer to that fatal limit. The very moment it crosses that 1.44 solar mass threshold, it's game over. Degeneracy pressure just fails instantly. Gravity wins. The entire core collapses in a fraction of a second. Temperatures skyrocket, and a wave of runaway fusion ignites the entire star all at once. The result is a Type A supernova, an explosion so mind-bogglingly bright it can outshine its entire home galaxy. But look, this isn't just some cool bit of cosmic trivia. This one number, this one limit, is fundamentally important to how we understand the universe, and it's even crucial to our own existence. So, why does it matter so much? Well, there are two huge reasons. First, these explosions are cosmic forges. They create and scatter all the heavy elements, like the iron that's in your blood right now, all across the galaxy. They're literally seeding the universe with the raw materials for planets and for life. And second, because every single one of these supernovas is triggered by the exact same mass, they all blow up with the same predictable brightness. This means they act as standard candles, a kind of cosmic yardstick that lets astronomers measure the distance to faraway galaxies and map out the expansion of the universe itself. It's really an amazing thought, isn't it? A single calculation, done by a young scientist on a boat, gave us this fundamental key to unlocking the secrets of the universe. It's not just a number. It's a trigger for creating the very stuff we're made of, and it's the ruler we use to measure the entire cosmos. That's a pretty powerful idea to sit with. The predictable, incredibly violent death of a star is actually one of our most important tools for understanding the living universe. It really makes you wonder, right? As we get better at spotting even more exotic and dramatic cosmic endings out there, what other secrets are just waiting for us in the grand finale of the stars?